So for the higher order system, so everything's written to save the time. So let's say there is a this kind of system, which is an example of our project. And let's say now the plant. This is the plant part, and this is the controller part. So we have I controller, and this is the transfer function. And the out of the log or multiply is that the multiplication becomes the addition. So it means that all the multiplication. So this one also becomes like this kind of the addition. So now it becomes very simple. Well, it's true for the magnitude as well as for the phase. So let's look at the magnitude first. So for the magnitude, um, for the pure integrator, so this is a merely constant. And then this is a pure integrator, and then again for the pure integrator, we can look at when the omega is very small, and also omega is very large. But for the pure integrator, it's simple. It's just something like this. It's 1 over omega and becomes due to the log characteristic, it becomes negative 20 log omega. For this part, so we can also discuss when the frequency is low, frequency is middle, and then frequency is high. And the frequency is low, this part, let's say A and B, A is negligible, so therefore it becomes almost zero. And about mid frequency, A and B, both of them are important. And about the mid frequency, which is omega, is about the same as this value. It becomes 1 over z plus 1, and then becomes negative 3 decibel. And in the high frequency, now the B part is negligible. You have only A part, means that it becomes again negative 20 log omega. And then we still have this value. So this value becomes constant minus 20 log omega. So if you look at the magnitude plot, this is the pure integrator. And then this is the, let's say, A, this is the pure integrator B, and then C. Similarly, we can calculate the B, and then calculate C. So when omega is 0, very small, the magnitude is almost 0. When the omega becomes high, about the cutoff frequency, where it's like negative, the frequency is the same as this frequency. The magnitude becomes negative 3 decibel, and starting from there, it is decay using negative 20 decibel per decade. The same thing for the other one, which is this guy, but now this frequency becomes 3779, and starting from there, it decay negative 20 decibel per decade. And then this is a pure integrator. What will you do is that you just add, and then this is the first part, which was the constant. So we even need, let's say D. This is the constant part, which was D. So what you need to do is like adding everything all together. So if you add 1 over S to this becomes something like this, just shifted. But starting from here, now you need to add this guy to the the blue part. So then now you have its original negative 20. Now you are adding negative 20 to negative 20. So it becomes negative 40. And then around this frequency, now you need to add this blue part, green part again. So you need to add negative 20, and then negative 20, and all three becomes negative 60. So now you have negative 60 decibel to decade. So, so once you have this kind of a table, what you can do it plotting the magnitude plot based according to the table, and then add everything. Then you have something like this plot. And then the important part is this the frequency where the slope is being changed. So in the exam, if it was asked, you should specify what is this frequency and then this slope. It's similar to the angle plot. So the angle at 8.55 is 0. So it's 0, and the 1 over j omega, arctangent 1 over j omega is nothing but negative 19 degrees. So it's simple. For this one, if the frequency is very, very low, this one is almost constant. So for low frequency, this is almost constant, so the angle becomes 0 degree. And about the frequency between 10 times lower, which is 380, and then 10 times about this frequency, the angle becomes let's just say, if omega is about this 30 this degree, the angle becomes 45 degree because it's arctangent 1 over 1. The angle, when the omega is very, very large, then it becomes, this part is more important, so it becomes about negative 90 degree. So this is being shown here. So when the angle is very small, about the 360, the angle for this part is also 0. And then it is 0 until it reaches about the, actually it's over here. It was a mistake. So it was 0 until 360, so 10 times lower. And then it is 0 until it's 10 times higher. So it's like about 380. This is 0, and then about 10 times higher, times 10, it becomes negative 90. So larger means that 10 times higher, and the lower it means that 10 times lower. In between, it is approximated as negative 45 degrees. So that is this part. That is, let's say this is, oops. This is A, B, C, D. This is C part, and then for the D part, it's similar. So until for this 3.6 K, it's 0, and then about 10 times higher that one, it becomes negative 90, and in between is 45 degrees. Then And then you don't forget about this till there's a negative 90 degree due to the J omega contribution. So now what you need to do is adding everything. So adding everything, and then starting from here, it decays negative 90. And then starting from here, you need to add this part to this part. So it becomes negative 90. And then starting from here again, now this becomes just negative 90, and then you have only this decay. It becomes negative 45, and then it looks like this. So there are 3 1 over j omega. So eventually it will go to negative 270 degrees. So starting from, because 1 over there is a pure integrator, it starts from negative 90 degrees. So this is the remark. So j omega is negative 90. If you did j omega square, it will be negative 180 because it's addition. And then if there is a the pure S, there is also, it's 90. So for higher order system, it's very simple. Just add what you have so far, and then you add using this body plot. So it's very useful tool to add everything, and then you get this plot.